Okay, so this session is about TLS 1.3 pen testers. It's going to be a fairly practical session, so it's not going to be talking about TLS 1.3 and sitting there going through the RFC and telling you about all the details. Instead, I'm going to be focusing very much on what the changes are going to impact your actual testing, so why things that you're accustomed to doing will stop working, and why you're going to miss things unless you start to take actual account of the changes. So let's start off with who I am. So my name is Richard Moore, and I'm a consultant at MWR. I've been working in security for a depressingly long time, particularly looking at, and almost everyone seems to be younger than me. So I've worked a lot with SSL and TLS. I've committed to OpenSSL. I've written a Python implementation. I've written tooling for testing it, and bored the life out of many people. So I've also talked about it at conferences like the BSides Manchester conference and released a bunch of tooling. So why are we actually interested in this? Well, first thing is I'm going to tell you a bit about what TLS 1.3 is and why it exists. So basically why we need it. And then cover off some of the basic changes, sort of really simple things. And then obviously, just to give an opportunity for things to go wrong and me to look like an idiot, I'll try and do some demos. Fortunately, not reliant on the Wi-Fi, so that's at least one bullet dodged. The next thing is, what else has changed? So there's a bit more detail, more stuff that I'm not going to cover in the initial set. And then some more demos, a bit about deployment, sort of when you can expect to see it, why you can expect to see it, and where you won't expect to see it. And then finally, a few things which, whilst they are theoretically available now, they don't really work yet, or they're not really practically deployed. So those changes are things that you'll probably be seeing in a year or so, or maybe sooner if you're on that kind of network. So to start off with, why do we need it? Well, TLS is basically, it's SSL, but dressed up. It's nothing special. A lot of it was designed 20 years ago, and unfortunately that shows. There's been a lot of evolution in thinking about how protocols should be designed, and thinking about what kind of protections are needed. There's been some thinking that's changed about the basics about how we put cryptography together. It also helps that TLS, well, SSL was developed basically by a couple of guys working at Netscape. Netscape at the time were just the biggest browser manufacturer, the biggest server manufacturer. They were kind of Google, but for their time. And sadly, they don't exist anymore, but they're where Firefox comes from, if any of you don't remember that far back. And they put together SSL as a way to do commerce on the internet. Because when the internet started, it wasn't encrypted, everything was open, and as a result, putting a shop on the internet was, well, it was a really bad idea, and everyone's credit cards would have got nicked. So we really need this stuff to be right, and sadly it wasn't. So there's been a lot of work gone in over the years to try and patch it up. So what we've been doing is basically playing whack-a-mole. That is sadly not every vulnerability. That's just some of them. So Heartbleed, that's an implementation flaw. That was affected some versions of OpenSSL, and it basically allowed you to access bits of server memory. As a result, you could get keys, decrypt the traffic, so you could see the traffic in plain text on some configurations. I remember sitting there watching people changing their passwords on vulnerable systems and seeing the new passwords go by. This was not good. Loads of certificates had to be changed because it also turned out that elements of the private key leaked, which was sufficient for people to be able to decrypt the traffic. So that was basically a major disaster in terms of internet security. Beast, boring, but adding Oracle attacks, these things are all in the protocol, and they're all detail. Another one, this one's compression. And then we've got PKI. So this is basically, first one is somebody getting into the web interfaces or the APIs used by a certificate authority to basically flog certificates. So they had an interface that allowed their suppliers, their resellers, to basically generate certs. He got in, made a bunch of his own. Not good. So basically he could pretend to be anybody. Last bit was an interesting case because the compromise was legal, entirely legal. What happened was they had an email server, it had its private key, everyone's all happy, all the traffic's great, it's all encrypted, except that then the government, or I think it was the States, got a warrant, said give us the key, and he fought it, failed, had to give up the key, and because his configuration was poor, it actually turned out that they were able to decrypt all the traffic, and therefore all of these supposedly secret emails were now open. And again, that's, built into the protocol. There's nothing there that can easily prevent that kind of thing. Protocol flaws. We've had another one was renegotiation. It turned out that over a decade after SSL and TLS were put together, that someone found there was a bug in the protocol and no one had noticed, and it turned out you could basically renegotiate, and there wasn't a proper binding between the old channel and the new channel, and somebody could jump in the middle. And that's very much an edge case and easy to turn off, but all these are indicating that it's really creaking at the edges. Poor use of Diffie-Hellman. Basically, after this breach, everyone started saying, oh, let's use Diffie-Hellman and that will solve this problem, give us forward secrecy. Unfortunately, then it turned out no one had looked at that code either, and that was all rubbish as well. And so you've got lots of systems that are configured with really weak Diffie-Hellman primes, and no protections in the system to prevent you. So, I was able to configure an Apache server to have a Diffie-Hellman prime, or I think it was 7 I used. Now, that is not particularly strong. There's no protections in place, and there was nothing to make it obvious that I just managed to make a colossal mistake. It doesn't tell you these things. At the time, the tooling for looking at that was poor, though it is getting a bit better these days. Things like SSL Labs will bring you up a nice report and tell you lots of stuff you're doing wrong, and that's great, but really, we shouldn't be relying on people to configure all this sort of arcane stuff. You've got the Mozilla config generator. It's fantastic. But why do we have that much config? Why are we giving so many people so much opportunity to shoot themselves and us in the foot? That's just a fundamental design error in the software and in the protocol. So they're trying to fix it. So some of these issues, going back years, CPC cipher issues. So that was where a load of these issues came from. This was known about in 2004, and it's still there. Because really, it can't be fixed. It's a fundamental problem with that mode, and because of the way they were basically ensuring the integrity of the data, that it wasn't being modified, there was no easy way to fix it. The only way to fix it is to layer on a whole other set of protocols, so another set of cipher suites. And all that means is the old ones are still there, and now we've got another bit. So basically, it just gives people another knob that they need to configure. This is not a sustainable way to approach things. So, yeah, these things, they weren't thought to be practical, but sadly, yeah, turns out they were. Who guessed? And then, weak ciphers. No one would ever enable those in production, but then, you look at things like SSL Labs, and you find out, well, the banks will, and everyone does by default, and all of the older software does, and Java does, and if you turn it off, then you find you actually can't connect to a lot of stuff. So it turns out you have to turn it on. So as a result, having these things in there is inherently risky, and it's basically a big mistake that, we're living with, and we're trying to make up for it now. The RSA key exchange was another mistake. But obviously, we didn't know that at the time. The lack of forward secrecy was the weakness there. So what it means is that if you get the private key, so those of you who have done testing or have done courses about testing will have seen things like sort of path manipulation attacks where you can effectively get files off a server, or you could compromise a server some other way. If you can get to the certificate, it's game over if you configure it that way, because you can then decrypt all the traffic. So everyone who's accessing that site, or has historically ever accessed that site if you recorded the encrypted traffic, is now compromised. Again, not good. The passive eavesdropping issue is what I'm talking about there. So effectively what you can do is Just monitor the traffic and then decrypt it. You don't need to actively man in the middle. So if you're familiar with Burp Suite or something like that, that's an intercepting proxy. It does an active attack, and that's quite a different approach. That will still work. So, TLS 1.3. They have some specific goals. And one was encrypt as much as possible. So that's great. Makes a lot of sense. Address any known weaknesses. Well, you'd hope so, wouldn't you? Be a bit stupid otherwise. Now this one's interesting. Change in the aim of the protocol. Previously, privacy was not a specific aim of the protocol. Confidentiality was, but that's not quite the same thing. So they're similar concepts, but not the same. So an example would be making information as unrecoverable as possible, making it so that eavesdropping is actively hard, not simply relying on the fact that somebody who's an active attacker can't intercept it. Another interesting thing was, in every other version, they just added new stuff. So TLS 1, 1.1, 1.2, each one just adds more things, which is more things to go wrong. And of course, it's bad enough that we're adding a whole new protocol, so 1.3, more things to go wrong as well, I admit. But at least this one is smaller. So what they did was they threw away a lot of the concepts that were in the old one and made it much, much tidier. And they actually started asking people about maybe how we could do this securely. Good start. So rather than all of the analysis being done after the fact, so 20 years of sort of whack-a-mole, what they said was, up front, let's look at it and let's analyze the hell out of it at this point in time, and as a result, what we can do is get a protocol that will actually be fit for purpose, rather than then having to go back and make 1.4, 1.5, and start patching it all up. So this is a really good change. So, what are they? Well, removing all of the old stuff. The non-ciphers, these are ciphers that don't encrypt. Why? I mean, what possible earthly use is that? But if you look at the TLS 1.2 spec, which was previously the very latest version, it still talked about them. So it's not like they were even just some little appendage that everyone had forgotten about. They were in the body of the text. They are insane. They're a massive foot gun. Fortunately, these days, people are no longer ignorant of them. So it used to be that you'd find them turned on quite a lot. So, doing a lot of internet scans, you would find loads of servers with them turned on. But, this is not good. RC4 and triple dares. RC4 is weak. We know it's weak. No good reason to use it these days. So, yeah, burn it with fire, kill it. Triple dares. This one's a bit harder, because it's not great. It's got a number of issues, but it's quite widely deployed. But the thing is, we've got better options these days, and we have a proper standard, so it's not like we need it for standards compliance. We have AES, which is kind of its replacement. So let's just go with that. So, yeah, again, kill it. Export ciphers. This was a thing back when the Americans were trying to prevent everyone having crypto except for themselves. They said that only banks were allowed to have strong crypto and everybody else had to have weakened crypto. This was not ideal, but as a result, what you found was that a lot of systems would have artificially weakened security, and this would be enabled by default. So again, not what you want. It's really not. RC2, single dares, these things are from the ARC. And then these ones which are weird. It's like these are ciphers that exist for particularly odd standards, or because somebody thought it was a good idea as a research project, and because of the lack of control over the standards and lack of control over the code bases, they've been accepted. Say they go into OpenSSL, they'll get in the default cipher string based on the list of what's secure, what's not, because they're not actively broken. But it's just more attack surface, more to go wrong. So, what does it mean for us as pen testers? Well, first thing is it means we don't have to report weak ciphers anymore. That is brilliant. So we can finally concentrate our effort on more interesting issues. We can write up things that people actually care about. We report weak ciphers, everyone goes, off. And that's fine, they need to switch it off. But why on earth are we finding these stuff at pen test? This should be getting caught much earlier, and it should not be our problem. And we hate writing it up. They hate reading it. Why are we wasting everybody's time? Let's just fix it. So we can't pad our pen tester reports out with noise anymore. So that is kind of bad, if you're weighing reports and sort of thinking, well, the value of the report is how many pages it is. Well, obviously it's a disaster because we can't pad the report. But really, is that offering value to the business? Not really. It's just window dressing. It's just making things look impressive. And these issues are the kind of issues where, whilst they're compliance failures, they're very rare that people actually get compromised this way. So nobody cares. We don't care. The customer doesn't care. We know we have to fix it. We all have to do it, but it's not interesting. Sadly, for now, they're going to have to support the old versions as well, so we're stuck with it for a while. But, it's going to get better. Another big change, cipher suites. Who's familiar with the concept of a cipher suite in TLS, earlier versions of TLS 1.2, etc.? Well, you should be, yes. Okay, so the cipher suite bundles together all of the information about a cipher. So it's the cipher, it's the MAC that is used to check some of the data effectively, it's the key negotiation strategy, it's how you prove your identity. So it's basically everything about how we're going to secure the connection, all bundled up into one tiny little number. And that number is just a reference into a list which is maintained as a standard. And then you negotiate the number, the server basically picks which one it wants, and then you end up with whatever they've said. And you're stuck with it. Well, that's been changed. So because we had, I think it was 340 last time I checked, different cipher suites in TLS 1.2, nobody needs that many. And half of them go away immediately because it used to include the certificate type. And everyone uses RSA certificates, or very slight number of people are starting to use elliptic curve certificates, but it's incredibly rare. It's effectively zero. And then there's the DSA certificates. I've never seen one in production. Maybe somebody has, but they are so rare as to be like unicorns. So let's just count them. The other thing they've taken out is the key exchange. So instead of saying whether we're going to use RSA for the key exchange or Diffie-Hellman for the key exchange, that's gone as well. We're always going to use the same thing. And in terms of cipher suites, we've gone from 340 odd to 5. And of those 5, some of them are actually the same, but with slight tweaks. So it's a massive reduction in the attack surface, and they're all using well-tested algorithms. The negotiation process is therefore much simpler, the risk is much simpler, and the number of things that cryptographers need to worry about is much smaller. And these are ones that they've already tested extensively. It's using what is thought to be the best standards in terms of doing things. Even the cryptographers seem to be in general agreement that it's being done right. They've actively gone out and tried to prove security. So this is all really good. So a bit more on some of this stuff later. All CBC cipher modes have gone. So they were previously, I would say, the most widely used ones, and that is now toast, because it's also been the biggest source of weakness. So it's always using this thing, AEAD. What that basically means is it encrypts it and preserves its integrity at the same time. So instead of having to worry about do we encrypt it and then ensure the integrity, or do we ensure the integrity and then encrypt it, it's always the same, and we do it together. It actually underneath is, there's a couple of ways you could do that, but instead we're just treating it as a black box and saying we're just going to do it. And that's always going to be the case. So that's a good change. So, padding on local flaws, which have been the bane of everybody's life, are gone. No more. Until somebody finds a whole new class of attack, we're pretty good. A handshake. So the handshake is what happens first. The client says hello, the server says hello, we agree on all the things, I'm going to do these ciphers, you can say these ones, and we say everything about what we want the connection to be. Well, that's, in the previous one, so much of that was unencrypted. So, just by looking at the traffic with Wireshark, you could see who's being talked to, because that was there in the server name indication. You could see who's being talked to again, because that was there in the certificate. You could see the public key. You could see details of the key exchange. So there's all sorts of information happening in public. Now, some of that information was getting leaked other ways because of DNS, for example, but, somebody else having a problem is not an excuse for us to have a problem, particularly when the whole goal of our protocol is to be secure. So this sort of information leakage is getting addressed. It's not perfect yet, and I'll talk about that at the end. The server certificate is public information, but equally there's no reason why people should be able to know which of the sites you are looking at. So there may be more than one site on a particular IP address, and there may be, there's no reason why you need to know that, so why should you know it? Privacy is one of our goals, so that's what we get. And TLS extensions, previously these were basically sent in the clear, well, they're not anymore. Great. So what that means is, if you look at it in Wireshark, the change cipherspec bit is where it's saying, I'm going to be encrypted from now on. And what you see is, I don't know if you've looked at handshake in Wireshark before, but you can see that basically you can't see anything. So what we've got is a situation where things are much better. So, how do we test it?
That's a question.
Yeah, of course.
How do you agree on the encryption for the handshake?
Okay, that's a complicated question. Some of that I'll actually cover later, but during the initial client hello, the client sends its key, or its component of the Diffie-Hellman key exchange, and the server then replies in basically its first packet as well. So from that point on, they both have sufficient information to be able to encrypt the traffic. So it's just moved much earlier by sending the information as soon as possible.
Okay. They've already kind of agreed that it's going to be Diffie-Hellman for the handshake.
Yeah, so basically the only handshake that is left is Diffie-Hellman. Yeah. Basically it's the only one. So it's Diffie-Hellman variants, but, it's basically Diffie-Hellman. So as a result, you've got the information you need, and therefore you can start encrypting pretty much from the get-go. So nice and simple, problem's been eliminated, and yeah, all good.
Cool. Thank you.
Okay, so fingers crossed this will not go wrong. On the other hand, you guys will probably have lots of fun if it does, so we'll see. Wonderful. I suspect this might be a software issue. Okay. So, yeah, it's stopped. It shouldn't be. It's not extending like it, no. What can I do about that? So I'm going to close that just in case that was it. So that's display port. Okay, and let's see if I can just move it instead. So it's only seeing my display, it's not seeing this at all. Right, okay, cool. Right. Okay, so, yeah, the demo gods are definitely here. So, let's just make sure so let's kill that. And so what I'm going to do is start off some servers. So this server is just an OpenSSL server, and it only supports TLS 1.3. So you can see that I've specified minus TLS 1.3. So that one's on port 3000. So there we go. And then I'm going to start another one that supports both 1.2 and 1.3. and that one I will start on port 3001. Okay, so if I load it up, we can see that it is working, so that's good. And 3002 also working, so great. So the server on 3002 supports both versions. The server on 3000 only supports SSL3. So we have lots of standard tools. So if I was to start doing test, I'd say localhost 3001, and I'm just going to run SSL scan because, you know, that's how we do things. But unfortunately, it can't connect. So, you know, if you're a pen tester or a script kiddie and you're just going to go, okay, what do I do now? You know, the tool doesn't work. Obviously, it's a problem with the tool because, you know, I'm perfect. It's never me. But, you know, it's not good. So what else can we do? Okay, well, we'll try a different tool. This is test SSL. Taking a while. So test SSL is a scary shell script, and it's really thorough, it's really good. Fortunately, there we go. Ooh. It says, you should not proceed as no protocol was detected. Oh dear. Maybe there isn't really a server and, you know, Firefox is lying to us. So effectively what we can say is that our tooling does not work. This is not good. And as a pen tester, this really matters because that's entire attack surfaces, potentially entire applications that you can't test. So, what are we going to do now? Well, let's fall back to SSLIs. And if I can remember the syntax for it, I think it's that one. Let's just double check. Yeah. SSLIs. Wow, so this has done something. Did it work? Sadly, because of the size, I've had to make the font so that you can see it clearly. But what you can see is that SSLIs actually did work. It didn't used to, but there was an update very recently. There's also been some changes going into the Git repository for test SSL, so that if you try it in the very latest versions with a TLS 1.3 server, what happens is it works briefly and then crashes. But you know, that's better. The good thing with these ones is, A, we found a tool that works, so we know that there is something we can do about it. And the other thing is that these have not been invisible failures. So, what happens if we try to do SSL scan on port 3002, which, as we recall, supported the old version and the new version? Well, we've got our results. Great. But it doesn't mention the fact that version 1.3 was never at all. So effectively, we've got a silent failure, which is even worse. So we think we've tested it properly, and we haven't. And that is not good. So, you know, we need to do better than that. So how can we test it? Well, an obvious answer is we can always fall back to OpenSSL, because we always can. So you can if we learn to spell localhost. So, okay. So that worked. Great. So that gives us a point of entry that we can always use that. The other thing that everyone always uses is burp. And when I started writing this presentation, the answer was that didn't work either. And they've released a new version now, so now the answer has changed. So it's not the only tool that changed during the writing of this talk. So several of them are gaining support. So for burp, you need to be using the latest version, which is version 2.1 that came out weekend before last, I think it was. And if you do, and this is probably going to be way too small for you to see, and it's Java, so it's not easy for me to fix. So I won't bother because you're not going to be able to read the text. But basically, if you're using TLS 1.3 and you're using Burp version 2.1, you'll be all right. The connection between Burp and the server can negotiate 1.3. The connection between your browser and Burp cannot. So that's quite confusing. So that's something to watch for. That if you look at what you negotiated in your browser, it will tell you the wrong thing. So, a few rough edges, but at least you can do something. You can configure all of this in the SSL settings in the Burp user options and project options. So if you say, specify custom cipher suites, for example, then I can demo that, you can still connect. So it's worth knowing that is feasible. We saw the SSL scan option with both versions. We saw that test SSL works. Oh, sorry, test SSL doesn't work. But test SSL has a different behavior if we test it against 3002. So this is another one. So 3002 supports both versions. And sadly this tool is quite slow. But what we would say is it does it right in the new version of this. We get loads of output, but yeah. So in this version, which is the version that's the latest version in Kali, it doesn't work, and it tells us about all of the versions that aren't there. It tells us 1.2 is there, but 1.3 doesn't come up at all. So if you're using the latest Kali version, we're no good. So a couple of things that we can do is we can just knock together some scripts, and I will release these when I'm next in the office, but they are really simple. So what this is doing is just telling us which ciphers are supported on TLS 1.3 really quickly, so it just lets us see what's going on. We can also do a similar test to see what versions are supported. So, I'm not quite sure why we're getting quite so many warnings today, but yeah, if I tidied up that so that there wasn't all the output from standard error, what you'd see is you get a list of which versions of TLS are supported. So just by using that script, you can just do a sanity check to make sure that you've not missed TLS 1.3 servers. And then if you have missed them, obviously you can validate ciphers. Validating the ciphers in a TLS 1.3 server is not a particularly productive activity, I have to say, because they're all good. Over time that may change, but it's more likely to be implementation flaws rather than protocol issues because of the amount of testing that's been done. Sadly, implementation flaws are not something that's going to go away. They can't be magically fixed by fixing the protocol. So, now, unfortunately, I have to click through the slides because oh, here we go again.
So when it's going into presentation mode.
Yeah, so see. Okay. Right. So right. So here we are. So this summarizes what we saw in the demo. So OpenSSL, obviously I was using it for the server, so we know it supports it. It does support all of the versions. SSL scan doesn't support. Test SSL on the latest Kali? No. Test SSL from GitHub? Yep, but it's buggy. SSLize works properly. Burp Suite? Yes, but only if you're using 2.1 and the latest Java. So basically, if you've got everything right, you can test this stuff properly, but it's really important to note that your tooling will not just sort it out for you. And if you're just used to blindly running SSL scanner and expecting to process the output after you've got back to your home base, it will not work, and you will miss things. So we've done those examples, so that's all good. So what else has changed? So we had the question about the key exchange. Well, the RSA key exchange has been removed, and instead we're now always using Diffie-Hellman. This was really widely used, but it lacks forward secrecy. What that means is that someone who steals the private key can decrypt all the traffic if they recorded it earlier. So I record all your traffic, it's all encrypted, I steal the key, and then I can decrypt it. That's no longer true. DSA certificates and key exchange, whatever, nobody used it, so who cares, gone. And this is the answer to the question from earlier. So the client key is sent in the client hello as an extension, which is what allows us to start encrypting things quite so early. So what does it mean? Yep.
Does that mean that if we do the DHCP exchange in that low, we've set up asymmetric before we've done auth?
Yes. But so what? You're not transmitting any sensitive data at that point.
Let's make sure I understood what you said.
Yeah. So we've always got forward secrecy, and you can't just take the traffic and decrypt it later. Wireshark can't decrypt it. It's a problem for us. And WAFs can't decrypt it. So if you've got a WAF, hello.
There was a thing published that Chrome and Mozilla would actually, for Windows, from the clients, if you set up the environment variables correctly.
I've got a demo of that coming up. And even
does that work with 1.3 now?
It does, yeah. And I'll even demo how you can do it with OpenSSL.
Alright.
So yeah, WAFs and proxies that are inspecting, they have to decrypt and re-encrypt. So basically you have to terminate the SSL properly and then re-encrypt it if you want it to remain encrypted. What that means is, for example, in a highly regulated industry, you can't just record the encrypted traffic and decrypt it later if you're going to use TLS 1.3. But I need to, because sometimes I want to do protocol analysis on the clients. And sometimes I want to do debugging, and sometimes we want to use the environment variable. So what you can do is you just set this environment variable, point it at a file, and say, this is where I want you to log the keys. And anything that's like Firefox that uses NSS, which is one of the crypto libraries, or Chrome, which is implemented itself, GNU TLS, which is another crypto library, all of them will log the information that you need in order to decrypt the traffic. And this isn't a massive security hole, because if someone's in a position to set environment variables on your system, you have already been compromised. So if they're in a position to do that, they could be compromising the client in other ways. So basically, whilst it sounds scary at first sight, you're already in trouble if that happens. So it doesn't really matter. The bad thing is that it doesn't work for OpenSSL. OpenSSL provides an API for extracting the information, but it doesn't support the environment variable because they thought, well, we'd rather be secure by default, even though what's the threat model they're securing against? Who knows? So we've got the callback that says, give us the keys. That's great. But how can we use it? Well, we could use a debugger and call it ourselves by hand, extract the keys. What a pain. But we can use LD preload to do hooking. This obviously will only work on Linux. I suspect you could do a similar thing via DLL injection on Windows, but I've never tried. And I was going to write a nice little tool for that to do as a demo. And then I thought, well, let's Google it first. Turns out the Wireshark guys have already done it. Awesome. So thank you, Peter Wu, for releasing this tool. What it will do is it'll let us hook in. It supports all sorts of different versions of OpenSSL, and it will tell us what the keys were for the traffic. Sadly, if the application statically links, which some do, then using the LD preload to hook into methods doesn't work. So it's not perfect, but it gives us a good start. So here we go again. So, excellent. So, we've got our servers running as before, and I am going to CD over to the Wireshark directory. And here I've already built the library. It's really easy. You cd to the right directory and type make. Not hard. And here is a command line to run it. So I'm specifying the file that we want it to write to as an environment variable. I'm setting the LD preload environment variable to say what DLL I want injecting. That's what DLL, what shared library I want injecting. Not on Windows today. And then I'm running the OpenSSL command line. Now, what's great is we've got Wireshark, which is a fantastic tool. So let's capture all the traffic. So that was me practicing this demo yesterday to make sure that it still works, because demos. So I've already configured OpenSSL. I've already configured Wireshark to look at the same file. So in the preferences, under protocols, we scroll down all the way. Well, a lot of protocols it supports. Somewhere down here. Yeah, here we go, SSL. So here, you can see that I've specified a file which contains the pre-master secret. It doesn't really in 1.3, it kind of doesn't work like that anymore, but it supports the information that we need to decrypt it. So I've already specified the same file that we're going to use, so in theory, this should work. But you know what they say about theory and practice. So let's bring this up. So we're going to run it. So, hello, SteelCon. So we've captured some traffic, which is good. You can see that it's a TLS 1.3 connection, or I hope you can see, I don't know, I've tried to make the fonts a bit bigger. But the interesting bit is, when I get to the application data packets, if I get the right ones, the decrypted tab, you can see it says hello SteelCon. So even though we're using a Diffie-Hellman key exchange, so we do have forward secrecy, even though we're using TLS 1.3, so we do have the shiny new stuff, we're still able to decrypt traffic, we're still able to do protocol analysis. But obviously, this wouldn't be something an actual attacker would be able to do trivially to us, but it means that for debugging purposes and for the purposes of performing testing, working out protocols and stuff, we still have a solution to the problem. So I think that's quite a good balance between security and the needs of actual confidentiality. So, let's see if this works again. Okay, so what else has changed? Well, version negotiation. There's always been a version negotiation mechanism since SSL. So basically, there's a version number in the client hello, and there's a version number at the record layer. So the record layer is basically the structure of how messages look, and the one in the handshake in the server, the client hello, is sort of usually the highest version the client supports. And the server then responds with a server hello containing the version that it actually is willing to talk. Now, that's great in theory, doesn't work. Because what was found was that if you tweak those numbers, and all of the middle boxes, so boxes on the internet that are decrypting traffic or passing traffic through, so inspecting it in some way, a sufficient portion of them were poorly written and didn't handle it correctly, so that when you change the numbers, what happens is everything breaks. So a lot of people in corporate environments would find that, in fact, a certain percentage of their connections would fail. And that's obviously no good, particularly since it's going to be really hard to debug. So instead what they've done is they've added a whole other version negotiation mechanism, which is another extension in the client hello. So you say, this is the versions I want to do. So nice and simple. Whether it'll work, who knows. I suspect that when the next version comes along, it'll turn out that people have been hard-coding that as well. They've introduced another feature called Grease, which basically tries to put random extensions in to try to reduce the chances of that. But I suspect what will happen is people will blacklist the extensions that have been reserved for that purpose, and we'll just try and decode everything else. So we'll probably be in the same mess again. But, you know, we can hope. Another big thing, early data. In terms of performance, SSL adds some round trips to the connection. So you already have your three-way handshake to establish a TCP connection. The latency of a round trip is actually the slowest bit. So sending data down the pipe is not slow. but the gap for waiting for it to come back is. So the fact that TLS adds more is obviously a bad thing from a performance point of view, and some of the people who were involved with TLS, particularly Google, for example, were really keen on trying to make it faster. So what they've added is a concept called early data. It's basically session resumption, but with bells on. So session resumption was a mechanism whereby the client remembered the details about a connection, reused them in a subsequent connection, and that allowed it to start up the crypto really quickly. So basically you could start knowing already the keys. Now, there's risks associated with that, but there's also advantages, as I say, because it makes things go faster. What's new is that now, in addition to that, you can throw some data in there. So you can throw a request in there. The bad thing with that is that data is not properly protected because of the issue that you referred to, which is that we don't know the authenticity at that point in time. So as a result, if you process that data, someone could replay it. So you can capture it and do it again and again and again. And if you are replaying that, then bad things could happen. Now, what's supposed to happen is, you all know that in HTTP, if it's a GET request, nothing's supposed to change. And we call that idempotent. It doesn't happen in practice. People do things do change. And that becomes very important here, because early data requires the same property, that it shouldn't change anything. And it should be replayable without making things any worse, or making any other changes. As a tester, I suspect that is going to be a rich vein of attacks on TLS 1.3, unless people decide that early data is just more hassle than it's worth. At the moment, it introduces some significant risks. Now, I'm a bit short on time, so I did have a demo, but I'll post development commands to do the demo on Twitter or something, and people can get the demo that way. So I think if I try to show it, then particularly with the issues we've had with the screens, it'll probably take a little bit too long. What the demo showed was basically that using OpenSSL, you can send a request with early data in there, and it will flag up to you if early data was used. So it's as simple as that. And what that means is that when you're performing a pen test, you can try putting a request in there, see if it happens, see if it gets processed, and if it does, then if that request is not something which should be repeatable, so if it can't be safely replayed, then you've found a vulnerability and you've got a nice finding to do in your report. If it says, I'm not supporting early data, then, great. It's compliant, but it's obviously less fun. But at least it means you can then move on and start testing the application proper and looking for more interesting things. So, as I say, I'm going to skip the demo and go to deployment. So, older versions of SSL and TLS were not widely deployed at the point of release. So basically it took forever for them to come out. TLS 1.3 has been different. A lot of people are already supporting it. So Cloudflare supports it and your browser supports it. So as a result, you're going to see it all the time. But in the internet, almost nothing will support only TLS 1.3. So that's good and bad. The good thing is you're able to test it. The bad thing is you may miss TLS 1.3 attack surfaces unless you start using the techniques I showed earlier. On the internal network, though, the story is different. On the internal network, you often control both endpoints. So say you've got a system whereby you've got the edges decrypting the traffic, and then you want to pass it around between microservices and things like that. Then the decrease in the number of round trips with TLS 1.3 makes it actually an attractive option. The increase in security makes it an attractive option. So as a result, on some internal networks, I suspect you're likely to see it before you're going to see it deployed as a standalone thing on the internet. And if you try to test one of those without using the right tools, as we've seen, what will happen is you'll go, well, I can't connect to it, and nothing will work. And whilst I've shown specific tools for testing SSL, don't forget that I've not looked at every other tool you use that uses SSL. So all of those have the potential for all this stuff as well. So you've got to think about your toolkits, and do you have everything in your toolkit sorted out so that it can support TLS 1.3? Because, as you can see, the list of things that support it, even F5 supports it, even Java. I mean, if you're behind Java, you're doing something wrong. So you've got to make sure that your toolkits are getting updated and that your tooling supports this stuff. So, as I said, internal services, that's where I think you'd like to see it first in terms of standalone TLS 1.3. In terms of what you see in production, you will already see it in most cases, or an awful lot of cases, on actual websites. If you're using the Mozilla TLS config generator, which is awesome, and if you're not using it, you should be, then if you choose the modern configuration, then as of the weekend before last, it will now generate you a TLS 1.3 config. And that's the config that is designed for where you control both endpoints. If, however, you're doing something on the internet, then you shouldn't use that, and you should use the intermediate config, which also supports 1.2. Leading edge obscure stuff. Pre-shared keys. It basically, you don't have to use certificates for authentication in TLS 1.3. This was available as an add-on in 1.2. I suspect it's going to become more prevalent, particularly with IoT, because it's basically lower overhead. Encrypted server name indication. What this is you encrypt the server name. Not a big deal. But if you're using something like Cloudflare, you're going to have lots of things on the same IP address, and that's what allows us to do this. I don't have time to go into the details, but the combination of that plus things like DNS over HTTPS means that all of a sudden passive monitoring and monitoring of what users are up to has become an awful lot harder. So as these things get more widely deployed, the amount of privacy that you've got is going to increase. And DTLS. DTLS is basically the UDP version, so it's the version for VoIP and situations like that. The 1.3 version is in draft. It's not released yet. The latest draft was, I think, on the 9th of July. So there's obviously work to do on that, but it's going to be coming fairly soon. And so the summary is TLS 1.3 is coming, and you should be aware of it as a pen tester, because otherwise you are going to miss things. So yeah, check your tooling. Your tooling is not naturally going to work. You just need to make sure that it works. But you've got to cross-check the results of your tooling and use things like OpenSSL directly in order to make sure that the results you're getting are correct. And that's it. So anyone got any questions? Scott?
Given that like you just shown and talked about then, there's the ability to decrypt forward secret sessions in TLS 1.3, why do we still see such resistance in things like ETLS?
Because they want to do it on the cheap. So basically, they think it's easier to reduce everybody else's security than to do the relatively small amount of extra work to add this to their tools. There is no good reason why we would see things like ETLS. ETLS is a weakened version of TLS 1.3 that was being pushed by enterprises in certain regulated sectors who wanted to do passive eavesdropping, even though it's a bad idea, and they thought that everybody else should basically let them. So, yeah, it's a bad idea, in my opinion. They have their reasons. Some of those reasons exist. Whether they're, the right balance is that's a matter of a judgment call. My feeling is that it is, better to secure it and then introduce the insecurity where necessary. And the fact that the hook is there to do it means there isn't a strong argument.
I'm confused about how some of the more obscure ciphers have been removed in TLS 1.3.
Yeah.
It strikes me that with only 5 combinations that are based on current, well-known, tried and tested technologies, that as technology progresses, and particularly with the advent of quantum computing as well, we're going to get into a situation where we start crossing these 5 off the list, the way we've done with RC4, various others, DES, for example. Doesn't it mean that we're putting all our eggs in one basket?
To an extent, yes. But part of it is, if you're going to do that, make sure you've got a really good basket. So these are protocols that have been heavily tested, so they're primitives that we know are really good. So there may be advances that would affect it, but there's no single advance that's likely to affect all of them, because AES is one of the primitives and SHA-20 is another one. So they're 2 fundamentally different approaches. So there is quite a significant amount of redundancy in there because of that. So in the event of some massive theoretical breakthrough, it's only going to affect one of them at a time. So that means that we've got some breathing room, even in the event that does happen. Answer the question? No?
What's your sort of answer to the sort of desire to not move to TLS 1.3 because it's too difficult, or it's encrypted, or I don't want to do this now?
That's a perfectly valid position. I mean, if you are using TLS 1.2 at its best, then, that's fine. It's perfectly good. But the configuration effort is significant. The amount of work you're going to have to do is large, and it's likely to get larger. What you're going to find is that everybody else is going to be moving towards 1.3, and if you don't, you're going to be the one that's left behind. 1.2 is going to be around for an awful long time. It's good. We've been talking about 1.1, 1.0 was released in, the first, 99, yeah? So, talking 20 years. That's the kind of lifespan these protocols are going to have. And TLS 1.2 is going to be effectively a long-term support release. It's going to be there for ages. So there's no immediate pressure to move there, but there are some significant advantages to doing so. So, why not? If you do it now, then, or at least start planning for it now, then you don't have to worry about it too much in the future. At the very least, you should start testing to make sure that things work properly.
And what about knocking old stuff off the list?
In what sense?
Like SSL3?
Well, yes, absolutely, you should be doing that. I'd say the majority of people have already done it on external networks. On internal networks, there's still a lot of work to do. But yeah, I mean, there is a lot of systems out there that only support the old stuff. But if you actually need old versions, and some people do, not for good reasons, but for reasons of legacy software and things, and start putting it into zones that are not accessible from the wider corporate network, isolate it, and then use jump boxes with RDP and things in order to allow safe access to them. To basically isolate those ancient systems, because, basically, if they need to support SSL3 and they need to support TLS 1.2 or 1.0, then, frankly, they've got a whole load of other problems as well, and you should start looking at those ones. Any other questions? Yeah.
So, previous architectures that may have used something like SNI proxy, where they keep private keys on backend servers and just pass through the encrypted flow based on SNI. Mm-hmm. Do those people need to now start implementing a proxy where they have private keys on the proxy server because of encrypted?
Yes. And I think we're out of time, so thank you very much, everyone.